Thank you for staying for the closing event. So I'm Alex, and I will talk to you about community detection in graphs. Some disclaimer: this lecture is pure theoretical, no code at all. I prepared some GitHub repository for you to play with graphs and some algorithms, but it's up to you. Okay, a few words about myself. I'm a data scientist at Hunters, which is a cybersecurity AI Israeli startup, like all the buzzwords, and we're hiring. So if you want to talk to me about graphs or AI or Hunters, you can reach me at this. So some agenda for today. I would like to expand a bit the motivation and some definitions of community detection, and then go over thoroughly two algorithms, the Louvain and the BigCLAM. And if you have questions, ask. I hope I'll be able to answer. Community detection in general. So we as machine learning people would like to cluster things. And given a graph, we would like to cluster it as well. Like each node can be in one group or several groups and with overlapping communities. But running clustering algorithms, like straightforward clustering algorithms, is hard, right? K-means won't work, or it would work, but not optimal, like not well. So we'd like to use some property of the network to learn this data, this clustering. So we would like to get a graph and do something like this. This is not overlapping community, but still. So it's all the community detection stuff started back in 50s when some PhD students, Zachary, was doing a PhD in social science, and he was studying some friendship in a karate club in his university. And what happened during his studies of this karate club, there was a big fight between two members of the club, and the graph split it into two. And what he thought was interesting question to ask is, how can we cut the graph by cutting the minimum number of edges, so we can split the graph into new clubs. So this is like the first example of how the social network properties can be predictive. There's also a shameful award for anyone who mentions this network in conventions. You get a small award. What do we do with community detection? Basically, if you work with graph in one point or another, you would like to cluster it and do a community detection. So in social networks, you would like to find communities of friends or anti-communities, like of enemies. You would like to cluster customers with similar interest in advertising. And the third one is a really interesting blog post from Silverford. And they're talking about detecting malicious networks using community detection on their graph. So there's like a variety of application for this. So what is actually a community? If we take a look of a group of nodes, so we can say they are a community if the links within this group are larger than outside the group, like the three ones here. Like you see there are many links inside and a few outside. And the way we measure this community, the strength of this community, of this partitioning, is something that is called modularity, which is calculated like this. Like modularity is the Q, and we have a disjoint group of communities. This is for non-overlapping communities. And we go over all group, and we count the number of edges within this group and subtract the expected number of edges within this group that we think that should be within this group. So we'll talk soon about what is the expected number, but like ideally, if we found a much bigger number than we expect, that some random deviation of this group, we found a community or anti-community if this number is smaller. So the expected number of edges, how do we find it? We'll define something that is called a null model. And given a graph with n nodes and m edges, we would like to construct a new graph G tag with the same distribution. And G graph is multigraph, which means that between two nodes, there can be few edges. And we will say that the expected number of edges between node I and j is the multiplication of their degrees, which is k sub I and k sub j, divided by 2m. And if you remember anything about graph theory, so this is quite like important formula, which means that if we sum all the degrees in graph, we'll get twice the number of edges because each edge is counted twice. So why is that formula correct? So if you think about it, if we look on edge I, it has ki spokes coming out of him, and edge node j, has kj spokes coming out of him. So we multiply the two, like this is the probability of them connecting divided by 2m. And we can verify this number by counting the number of edges in the graph. So we divide it by 2 here because we count each edge twice. Then we sum all the i's, all the j's, and this number. 1 divided by 2m is going outside of the equation. And then we're left with two expressions similar to this. So we get m, which is actually the number of edges. So this formula is probably correct. So another way to think of modularity is the second formula, the blue one. So given a graph and a subjoint group of communities, we'll go over all the communities and we'll go over all the nodes in these communities, and we'll set aij to be the number of edges between node I and node j, and subtract the expected number. And we normalize it by 2m, which means that basically this number is between -1 and 1, right? If we don't expect any edges, so we'll just sum all the edges together, all the edges, and we'll get 1. And the other way around, we'll get -1. So modularity range between -1 and 1. And if it's positive, it means that we found more edges in a community than we expected, which means we found something significant. And as a rule of thumb, 0.3 and 0.7 means that we found some significant community. And if the value is negative, then the number of expected edges, like we found less than expected. So we found an anti-community, a community of enemies, like if we're talking about social network. So the idea is to maximize the modularity, and that's how we find the different communities. And this brings us to our first algorithm, the Louvain algorithm, which is called after a university in Belgium, I think. And it's pretty fast. It runs in n log n, which is like quicksort fast. And it outputs a few levels of communities, as we can see in this diagram. At the first level, we have only nodes. At the second level, we have like the small circles of community. Then we have bigger communities until we have the whole graph. The important thing to remember is that it does not provide us the optimal answer, because finding optimal modularity is hard. It's NP hard. So it finds some optimization for this problem. And it runs multiple times in two phases. The first phase, we try to find the optimized modularity by doing some small changes. We ask each node, if we move this node to some neighbor community, will we gain something in the modularity? And if so, we'll move it. And after we do not have any more nodes to move, we'll run phase 2. We'll aggregate these nodes together into a supernode and do it run it over and over until we converge. So visually, it looks something like this. We start with a graph, then we identify the communities, like red community and blue and yellow. After we find them, we aggregate the communities into 4 nodes because there are 4 communities. We sum their edges, their inside edges and their outside edges, and run this algorithm again. Yeah.
So you actually get a hierarchical structure, right?
Yeah. This is one of the coolest things about this algorithm, that you can have a few layers of communities.
Why do you need to do multiple passes? Can't you just stop after the first pass and you have all your clusters?
If you want, like you don't have to do the second phase. You can do the first, but like it's pretty quick, so why not? So the partitioning part. So for each node, we perform 2 calculations. We try to put it in the communities of its neighbors, and then we find the one that gives us the largest gain in delta Q, which is the delta modularity. And we run this part until we don't have anything to gain. So this is quite difficult formula. I don't want to explain it all. I just want to explain the idea of it. The delta Q, when we move node I into community C, is the subtract of the community of the node I going into C minus its previous value, like the modularity before and modularity after minus the modularity before. And then we do this part. We asking ourselves how much we lose when we're moving node this same node from C to D, and delta D is the actually it should be minus there, but minus the modularity. And we can think of this calculation more easily if we think of our graph as a 3-node graph. We have our node I, the red one, the rest of the community, and the rest of the graph. So this makes the calculation a bit easier. And phase 2, we already talked about it. Like we aggregate all the nodes, we sum the edges, we sum the inner edges and outer edges, and we run. So basically, our output algorithm, like our algorithm looks like this. We start with each node in its own community. We ask which one will gain the most, get the first layer of communities, aggregate, and so on, until we get the whole graph. This is the Louvain algorithm, which is cool, but it works only on non-overlapping communities, which not really like the real data, right? So our real data doesn't look like the left graph, is more like the right one. We have overlapping communities, and even more like this one. This is like Facebook social data of some guy, and we have his high school friends and company and Stanford squash and baseball team, and there are a lot of overlappings, and these communities, Louvain algorithm won't find it. So what we will do now, we'll define a new null random graph model, which will help us to achieve this goal. And the new model is called affiliation graph model, AGM. And we'll talk about this model in a bit, but the idea is, given this AGM, we would like it to generate a graph as similar to our graph, and we'll take the closest one to our graph, and this will represent our communities. So the AGM looks something like this, where it's a bipart graph with a few parameters. On one hand, on the lower side, we have the nodes. On the upper side, we have the communities. Here we have two communities, and the blue nodes are connected to community A, and the green into B, and red into both. And we have the probability, there are PA and PB, which is the probability of the nodes to link with each other within the community, right? And given this model, we can generate a graph, which is quite easy because we take all the nodes as is, and then we flip a coin for the connection within each community. And if node belongs to a few communities, we'll like flip a few coins. And we can see that this AGM model is quite flexible because it can describe multiple communities. It can describe overlapping or nested or not overlapping, like the Louvain. Like any type of community will work here.
Do you need to ask it for like how many communities there are, or is it?
No. So these parts are the parameters of the model, right? So the V and the C and the M and the P, they're all parameters of the model.
Okay.
So given this model, it's quite easy for us to generate a graph, some graph. But it's not that interesting because we want the other way around, right? We have a graph and we want to generate a model, and that's how we can find the communities. And let's see how we will do it. So this is how we'll do it. Yeah. So we would like to get a model that generates graph, and then we will ask ourselves how close this new generated graph G tag is close to our graph G. And we go over all the models and we'll find the best one. And that's how we'll get an approximation as close to our graph and describe the community, get the model that describes our graph the best. Right? Like if you need to remember anything from this lecture, it's like this stuff, because it's a real cool trick. And for that, we need to understand how we do two things. The first thing is efficiently calculating the probability of a graph given a model and maximizing over G, which is using gradient descent. Right, this is no trick, but gradient descent. So given G and F, we would like to calculate the likelihood of F generated G. So our graph looks like this. We have zeros and ones. This is its adjacency matrix. Zeros represent no nodes, ones represent nodes. And our model looks like this because we have this flip of coins, right?
It's unweighted.
Sorry?
So it's an unweighted graph?
Unweighted, but I think, actually, I'm not sure if it will work with weighted. I'm pretty sure it will. But in this example, it's not unweighted. So we'll do something like this, right? We'll get the product of all the probabilities of U and V in the graph in the model, and multiply it by all the probability of U and V not in the graph, like the U and V from there. And then we'll get some matrix, and then we'll see how close it is to our model. So working with this kind of bipart graph is hard. In order to make our life a bit easier, we'll define FUA, which is like a number of the membership strength of node U to community A. And it's 0 if it doesn't belong. And if we go over all the communities, we get a vector FU, which is like a row vector of all the memberships. So probability of nodes U and V to be for a membership is like 1 minus the exponent of dot product of these vectors. If you think about it, we have two vectors. We're doing dot product, so we sum the multiplications. We get we get values for the places they both belong to. So this is like 1 minus exponent will be a small number, and it will be proportional to the strength of the membership. And then we'll take this multiplication and we'll apply log on both sides, because doing numeric calculation on real small numbers is quite unstable. So we apply log, and now we're like in log likelihood, and the multiplications become sums. So basically, this is not really important. We're doing a gradient descent, and we'll select the f that we're making small changes in f. But the idea is to find a model that is generate graph as close to ours, and that's how we get the affiliation model that describes our communities the best. And basically, that's it. So the first point here is my GitHub. You can find the Louvain algorithm example and a graph that I created. You can play with it a bit. The second is a really good lecture from Stanford, which I used to make this one. So it talks about about pretty much stuff that I talk, but much more thoroughly. And the slides for this lecture and the paper for BigCLAM is also an interesting one. So thank you.
So you defined the modularity score for disjoint partition.
Yeah.
Can we somehow extend it to the overlap thing?
Not that I'm pretty sure you can. I'm not aware, but I'm not like an expert in this area. Yeah, there's a lot more algorithms. These are just two examples. There are algorithms that use memberships of the edges and like weird stuff. Like this is like pretty basic things.
Is there some way to include metadata of each of the nodes in the graph? Like, I assume you don't use it as is, but you have additional metadata.
What kind of metadata?
I don't know if it's like users that, it's not only the connection between them, it's like maybe if they live in the same country.
Yeah, but then like these methods are pretty general that will work on any graph. If you have like more specific graph that maybe you have like geolocation or different kinds of nodes also, right? If you have I don't know, if you're talking about advertising networks, so you have products and you have customers, so then you'll need to do adaptation to these algorithms to your network. Like this probably won't work as well on a network with different kinds of nodes and different kinds of edges, right?
I think that as long as you can like try to model a similarity between two nodes, and set that as the weight between them rather than like the value of the.
Yeah, probably that's an interesting idea. Thank you. Thank you.